Hi class, this is Sir Alex Basco and welcome to General Physics 2. Today we are going to discuss lesson 6, which is all about electric flux. It's still related from our previous lesson, electric field, which is lesson 5, wherein we learn how to measure the magnitude of electric field as well as measure the electrostatic force using the electric field. This time what we are going to measure is electric flux, which is basically the density or how much electric field is passing through a surface. Also, what we are going to discuss today is a phenomenon called the electrostatic shielding created by Faraday cages. So at the end of today's lesson, what I want everyone be able to do is learn how to calculate electric flux. But before we can do that, let's discuss something called electrostatic shielding. And we will do that by first examining this following situation. Have you ever asked yourself, why is it hard to get signal inside an elevator? You might have experienced this yourself, wherein when you went inside an elevator, you find it difficult to receive text messages or even phone calls, and you would notice that there is no signal on your phone. Another situation that is still related, although it may not be apparent seeing it firsthand, is how is it possible for people to be protected inside an airplane when there is a lightning strike? The same phenomenon can be thought of for cars. When you are driving through a storm and there are some lightning strikes, how is it possible for the car, for the person driving the car, to be protected from these lightning strikes despite having a metal car? So how is that possible? Well, it's a phenomenon called the electrostatic shielding, and it is observed first by Michael Faraday when he created what we call the Faraday cages. What the Faraday cages does is it creates a counteracting field inside or in the interior of the cage, which basically blocks the electric field coming from the external source. What do we mean by that? So let's have this for example. So think of this box right here as your Faraday cage, and let me use my pen. These black arrows right here are basically your electric field, so that's your E right there, and this is your Faraday cage. And you can think of your Faraday cage can be your airplane, your car, or even the elevator. Okay, so what happens is this: when this electric field, which is external in source, so it's coming from the outside of the cage, when it passes onto a Faraday cage, or when it acts onto a Faraday cage, what happens is that the Faraday cage, the charges inside starts to rearrange. And as you can see, these smaller circles right here, which are negative charge, moved onto the side closer to the positive source of your external electric field. What happens is these sides become electrically negatively charged, and this sides becomes more positively charged. And we know that because same signs repel while the opposite signs attract. The positive side here, or the positive sign of your external electric force or electric field, attracts the charges, the negative charges from your Faraday cage. And then also this positive side basically pushes the positive, not only attracts but also kind of pushes the positive charges of that Faraday cage. Although not a lot of the positive moves, it's much more difficult for them to move. It's much more easier for the negative charges to move. The same thing here, these negative charge from your external source, this external electric field, kind of like push away these negative charges on your Faraday cage. What happens is it creates a negative side here and a positive side here. And what happens is that inside the Faraday cage, it creates another internal electric field. So as you can see, there would be red lines that is going in the opposite direction. So what happens is that your external electric field going towards this direction So you have an external field going towards this direction, which are the black lines, and then you have this is external coming from the outside source, and then you have another electric field which is internal, which is originating from the shifted charges of your cage, creates another electric field that is in the opposite direction. And what happens, since these are both vector quantities, is that they cancel each other. And what happens inside of your Faraday cage is that it's basically neutral. There is no electric field inside, and that is true for a lot of things. So, example, let's go back to the question: why is it hard for you to get a signal inside the elevator? Well, this is what's happening when you go inside the elevator and the elevator closes. The elevator creates an internal electric field that is going in the opposite direction of the signal wherein your phone needs to connect in order for you to make phone calls or even send messages. So what happens inside is you don't get any signal. The same is true for cars and airplanes. When airplanes fly and there's a lightning strike, the lightning strike is a type of electric, or it creates an electric field because it's a charge. So what happens is that the charges on the plane comes are rearranged in such a way that inside the airplane it basically becomes neutral. So that's what we call electrostatic shielding. I hope it's clear. If you guys have any question about this, you guys do not forget to ask me any question. Okay, just shoot me a message. But how is this related to electric flux? Well, basically, electric flux is a measure of how much electric field flows through an area. When we say an area, it could be a flat surface, or just think of it as a flat surface. You might be asking what does flux mean? It's a Latin word that comes it's a word that comes from the Latin word fluxus, which means flow. So you may think of electric field as flowing or passing onto a surface or onto a area. Okay, so electric flux is basically a measure on how much electric field is passing through an area. So for example, you have a box right here, and these red lines right here are your electric field. And as this electric field passes onto this surface right here, this one face of your box, then that is, if you measure how much electric field passes onto that box, or to that face of the box, then that's what we call an electric flux. Okay, so that is what we're going to do: measure how much electric field is passing onto a surface. Although I want you guys to remember that electric field actually does not flow, no? But it helps us visualize what is happening. Also, it will help us understand when we start talking about Gauss's law, which is our lesson 7. Okay, so I just want you guys to remember electric field does not flow, but we just say electric flux in order for us to help visualize it and helps us understand easily what we are talking about. But how are we going to measure this? Well, we have a mathematical equation. Electric flux is basically the dot product of the electric field and area vector. An area vector is a vector that will always be perpendicular to your surface area. Electric field, we've discussed what electric field is. So doing a dot product for these two vectors, I'm not sure if you guys are familiar. Dot product is basically a multiplication of your electric field and an area vector, and the angle between these two vectors, that is the dot product. So mathematically, this is your equation. So this is phi. So this is Greek letter phi, which we use to denote electric flux. Phi is equals to the electric field multiplied or dot product your vector area. and then it's basically a product of your electric field and your vector area cosine the angle between the E and the A. Okay, wherein your E is your electric field, A is your surface area, and angle is the angle between your E and your area vector. So let's explain that much further, but before I can do that, let's move on to notes. Okay, so electric flux, like I've mentioned, electric flux is basically how much electric field is flowing onto an area. So think of this parallelogram here, or this rectangle right here, as your area. And this area has what we call an N. An N is what I will call an area vector. This area vector will always be perpendicular to your surface. It will always be perpendicular to surface. And another thing about this N is its magnitude is always equal to A, or is equals to the area of your surface. Area of surface. So that's one thing that I want you guys to remember about your area vector. I used the letter N because area vector is also known as the normal vector. So every time I said area vector or normal vector or N, that's what I'm talking about. It is a vector that is always perpendicular to your surface, meaning it is always 90 degrees to the surface, and its magnitude will always be equal to the surface or to the area of your surface. So we have various equations to measure area. If you have a square, that's basically side times side. If you have a rectangle, it is basically length times width. If you have a triangle, it's 1/2 BH. So that is an area. And the magnitude of that area vector will always be equal to the area surface. And then you have E, wherein it is your electric field. We've talked about that. Okay, so how are we going to measure the electric flux? How are we going to measure the electric flux? Well, like I've mentioned, electric flux will always be the dot product between, it's the dot product between your E and N. Okay, so usually the equation would be electric flux is equals to E dot product N, but we know that N will always be equal to A, right? So we can rewrite this as E dot product A. Okay, and in order for us to measure the dot product, what we want to do is to identify the angle between your N and your E. So this would be E times A cosine the angle between the N and the E. Okay, so this is your equation on how to measure electric flux. Okay, so there's some things that I want you guys to remember. So I'm gonna take this area right here, and then I'm gonna look at it sideways. So think of this as basically a flat sheet of metal, or it could be a paper. But let's think of this as a flat sheet of metal. And if I look at the flat surface, what I would say is basically something like this. So let me draw. So I would say something like this, right? So this is my surface this is my surface area, or this is basically my area. And what I would say next is, if I look here, the normal will always be perpendicular to my surface. So my normal would look something like this. Right? Because it will always have to be perpendicular to my surface. And then what if I look at my E? So my E will always should be uniform, so it will always go on to this direction. Let me redo that. So let me just change this color so that we know this is E. E is purple. Okay, this is your E and this is your N. Let me order to the back. There you go. Okay, this is my E and this is my N. So this is basically this one, right? Okay. So what I want you guys to notice now, if my area, if my flat sheet is basically perpendicular also to my E, so if surface is perpendicular to E, the electric flux is maximized. Okay, so when my surface, this is my surface, is also perpendicular to E, my electric flux is maximized, meaning I have the maximum amount of electric field that could pass on to my surface. What this means is that my N and E are parallel to each other. So when your N and your E are parallel, it means the angle between them is either 0 degrees or 180 degrees. So if I'm going to measure this, my equation would be something like the electric flux is equals to E, and then I have my dot product onto N, but remember N will always be equal to A, so I would have A and then cosine, let's say 0 degrees. Now remember, cosine 0 degrees is actually equal to 1. So what this means is that EA cosine 0 degrees, or when my N and my E are parallel unto each other, it will always be equal just to electric flux is equals to EA. So this is my equation, or this is the equation that I want to use if my surface is perpendicular to E, or basically if my N is parallel to E. Okay, so surface is perpendicular to E, it means E is 90 degrees onto the surface, or that the N and the E are parallel to each other. So that makes this my equation, and this means that my electric flux is maximized. So let's take another example wherein I make my surface lying flat. So I'm going to take my surface again, and this time what I'm going to do is I'm going to lay it flat on the floor. And what I'm going to do is I will have my electric flux is still on the same, or going onto the same direction. So my electric flux is basically going in the same, or in the same direction. Let me just change this color. There you go. And what happens is that my N will always be what? Perpendicular to my surface. So my N right now should be going towards this way. right? So this is my E, and this is my N. Again, my N will always be perpendicular to my surface, and this is my surface. And what you're seeing right now is that when surface is parallel to E, basically the electric flux will always be 0, because what that means is that N and E are perpendicular. And in order for me to measure electric flux, it will always be the dot product between my N and my E, right? So what happens is that if N and E are perpendicular, that means that my angle will always be 90 degrees. And cosine of 90 degrees is always gonna be 0. So if my equation is like this, EA cosine 90 degrees, so that's basically EA multiplied by 0, and it will always be 0. Okay, so my surface is maximized or my electric flux is maximized if my surface is perpendicular to E, which makes my area vector parallel to E. And my electric flux will always be 0, meaning the electric flux is not passing through the surface, right? So there is no electric flux passing through the surface, and that makes my normal perpendicular to my E. Cosine 90 degrees will always gonna be 0. So the flux when your surface is parallel to E will always gonna be 0. So these are the things that I want you guys to remember about electric flux. So what we are measuring is the amount of electric field, or E, that passes onto a surface. So now let's try and solve some sample problems. Let's go on to our sample problem number 1. So for sample problem number 1, I have a flat surface of an area, or with an area of 1.25 meter squared. So let's write that as my first given. So for our first sample problem, I have an area that is equal to 1.25 meter squared, right? And then it is rotated through a uniform horizontal electric field of 5 newtons per coulomb. They gave me the magnitude of my E, which is equals to 5 newtons per coulomb. What is the electric flux? So what is being asked right here? What is the electric flux if the surface is A, parallel, and B, perpendicular to the electric field? So what is my electric field if my surface is parallel? So I'm just gonna write parallel to my electric field. And what if my surface is perpendicular to the electric field? So the formula that we are going to use is the same formula that we discussed earlier, wherein electric flux is equals to E dot product A, or this is equal to E cosine, or EA cosine angle. So this angle is between the angle of your normal vector, or your area vector, and your E. So let's write our solution. So let's begin by solving a electric flux when the surface is parallel to the electric field. So what that means is that I have a surface. This is let's think of this as my surface right here. So that is my surface. Maybe let's try and use this instead, so it's flat. So I have my surface, Okay. True. So this is my surface, right? That's my flat surface. And then I know that this surface is parallel to the electric field. So meaning the direction of my electric field is basically going parallel. So let me just change this color. So this is my E. What that means is that my N should be always perpendicular to my surface. So my N should be going this way. This is my N. So what that means is that if my surface and my E are parallel to each other, my N and my E are perpendicular to each other. And we've discussed this earlier. So if my A and my E are parallel to each other, which would give me E A cosine, and the angle between my N and my E is 90 degrees. We discussed earlier, 90 degrees cosine 90 degrees is equals to 0. Therefore, my electric flux is actually equal to, even if I write this is 5 newtons per coulomb multiplied by 125 meters squared multiplied by 0. That is all 0. So that is my answer. My electric flux is equals to 0 if my surface and my E are parallel to each other. As for letter B, wherein my surface is perpendicular to my electric field. So if I'm going to draw that, I'm going to have my surface like that. And this surface is perpendicular to your E. There you go. Sorry. There you go. So draw that again. Okay. So this E is perpendicular to my, this should be purple. There you go. Oh no. This should be purple. Okay, that is my E. So my surface and my E are perpendicular to each other, which means that my normal is what? Parallel to my normal is parallel to my electric field. So if I'm going to measure this, electric flux is equals to EA cosine. My N is parallel to E. That means this is 0. Cosine 0 is 1. So this is cosine 0 is equals to 1. So this is basically E is 5 newtons per coulomb multiplied by 1.25 meters squared multiplied by 1. So electric flux is equals to 6.25 Newton meters squared per coulomb. So that is my answer for sample problem number 1. So again, if my surface is parallel to my E, which means my N is perpendicular to E, I have 0 electric flux. But if my surface is perpendicular to my E, which makes my normal or my area vector parallel to E, this will give me the maximum electric flux. Okay, so I hope that is clear. If you guys have any question about this, do not hesitate to message me. Now let's go on to sample problem number 2. Find the flux through the top left and right side of the cube of side 0.5 meter when placed in a horizontal uniform electric field of 8.0 newtons per coulomb directed to the right. Okay, so let's try this. So let's write our given first. So we are given a cube, and according to this cube has side that is equal to, let me just erase that. Okay, so I have been given a cube. The side of the cube is equals to 0.5 meters. And they also give me the magnitude of my electric field, which is equals to 8 Newton per coulomb, 8.0 Newton per coulomb. And what is being asked? So basically what it's asking me is find the electric flux at the top. So find the electric flux at the top side. So electric flux top. They also want me to find the electric flux on the left side. On the left. The electric flux on the right side. So those are the three things that they want me to find. And that my electric flux is going or always directed to the right. So it's going from left to right. What are the formula that I'm going to use? Formula is the same. Electric flux is equals to EA cosine theta. Solution. So what I want to do first is to find my area. But for the area here, the area of a cube is different. Area of a cube is S cube. What I want to find is the area of my surface. And I have, they asked me to look for the flux for three surfaces. The left side, the top side, and the right side. So meaning I only have to find the surface of this side, not the whole cube. Okay, so since this is a cube, the surface or the face of the top, left, and right is basically a square, right? And the side length is what? 0.5 meters. So in order for me to find the area of a square, this is basically side times side, or S squared. So that's basically 0.5 meter squared. So the area of my square, or my left side, my top side, and my right side is equal to 0.25 meter squared. Next, what I'm gonna do now, letter B, is let's find the electric flux on the top side. And as you can see, for the top side, my electric flux is going towards this way, right? And my top is also lying towards this way, which makes my normal this way. And as you can see, my surface is parallel to my E, which means my area vector, or my normal vector, is perpendicular to my E. So that gives me, we've discussed this before, so my electric flux is equals to EA. The angle between my N and my E is 90 degrees, cosine 90 degrees, and I know that cosine 90 degrees is 0, which means that my E, which is 8 newtons per coulomb, multiplied my A, which is 0.25 meters squared, multiplied by 0. Therefore, my electric flux at the top is 0. So it means I don't have any electric flux or electric field passing onto my top side. Now let's move on to the left side. Well, if I look at the picture, my left side is this way. So I'm gonna look at it this way. This is my left side. And I know that the normal of my left side should face this way. Why should it face that way? Well, it's because it's a cube. I have to go externally. I have to go going outside. Therefore, the end on my top should never go inside the box. It should go outside. As for my left side, the end should go that way. As for my right side, it should go this way. So you should follow the direction of the end for closed surfaces. For closed surfaces, you should follow the direction that is going towards the outside of your enclosed surface. So as for the left side, it should be going that way. But my E is going towards this way. So my surface is perpendicular to my E, which makes my N parallel to my E, right? So what happens is that my electric flux on the left is equals to EA cosine 180 degrees. And cosine 180 degrees is actually equal to -1. So this is what we are going to get is basically E is 8 newtons per coulomb multiplied by 0.25 meters squared multiplied by -1. And this is actually equal to -2 Newton meters squared per coulomb. Okay, and lastly, we're going to do is we have our surface that is right, and my normal should go this way, and my E should also go this way. So my surface and my E are perpendicular to each other, which makes my N and my E parallel to each other. So the flux on the right side is equals to E cosine or EA cosine 0 degrees. And cosine 0 degrees is what? Is equals to 1. So this will make 8 newtons per coulomb multiplied by 0.25 meters squared multiplied by 1. And this will give that the electric flux on the right side is equals to 2 Newton meters squared per coulomb. So that is the electric flux. So again, if you have an open surface like this, you can actually choose whichever normal you want to use. But if you have a enclosed surface or 3D shape like this, your normal should always be directed towards going outside of that object. That's why my N is going towards the top. So my N is going towards the left for the left side, and my N is going towards the right for the right side. So if I measure the electric flux on the bottom side, my N should be going downwards, right? So I hope you guys it's clear. If you guys have any question about electric flux and anything else on this lesson, do not hesitate to message me. Thank you so much, guys, and may you guys have a great day.